When people first hear that an AI system learns from data, it can sound almost magical, like the data is simply fuel and the model is the engine that turns it into smart outcomes. The reality is more like cooking for someone with allergies. The ingredients matter as much as the recipe, and the wrong ingredient can cause harm even if the cook has good intentions. This lesson is about learning how to judge whether the data going into an AI system is appropriate for the intended purpose, whether it contains bias risk that could lead to unfair outcomes, and whether it fits privacy expectations and rules. That might sound like three separate jobs, but they are closely connected because what makes data useful is tied to who it represents, what it reveals, and how it will be used. By the end, you should be able to listen to a description of an AI project and ask the right practical questions about data inputs, even if you have never built a model or studied advanced math. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A helpful starting point is to understand what data input requirements really mean, because people often confuse them with a shopping list of fields like name, age, or purchase history. Requirements are bigger than fields. They describe what kind of information is needed, where it should come from, how fresh it must be, how accurate it must be, and what it must not contain. If a team says they want to predict whether a loan applicant can repay, the inputs should relate to repayment ability, not unrelated characteristics that create unfairness or privacy trouble. If the goal is to detect unusual logins, inputs might include device patterns and sign-in timing, not personal messages or unrelated browsing history. Appropriateness is the idea that the data matches the goal and can reasonably support the decision being made. When data is not appropriate, the model may still produce an answer, but it can be meaningless, misleading, or harmful in a way that looks confident. Appropriateness also includes context, because the same data element can be reasonable in one setting and problematic in another. A shipping address may be appropriate for delivering a package, but it may be inappropriate if used to infer someone's income level or neighborhood risk as part of a decision about eligibility. Even a seemingly neutral feature like zip code can act as a proxy for race or economic status depending on where you live, which means appropriateness cannot be judged only by the label of a field. Beginners sometimes assume that if the data is available, it must be fair game to use, but availability is not the same as legitimacy. AI projects often grow from whatever data is easiest to collect, and that creates quiet drift from the original purpose into broader profiling. Evaluating appropriateness means checking that the data is necessary for the purpose, not just convenient, and that the purpose itself is clearly defined. Once you have a purpose in mind, you can evaluate appropriateness by asking plain questions that do not require technical jargon. What decision will be made using the model's output, and what happens to a person if the model is wrong? Who is affected, and how serious is the impact, such as being denied something, investigated, suspended, or placed under extra scrutiny? What time window does the data represent? Because old data can encode outdated realities, like policy changes, economic shifts, or changes in user behavior. How will missing or messy data be handled? Because real-world data is often incomplete, and the way gaps are filled can introduce hidden assumptions. Finally, what human judgment remains? Because a model used as a suggestion tool is different from a model used as an automatic gatekeeper. These questions help you decide if the input requirements are reasonable for the claim being made. Bias risk is the next layer, and it is important to treat it as a predictable property of data, not a moral flaw in people. Bias in this context means systematic patterns that cause the model to perform differently for different groups, often because the data reflects unequal history, unequal measurement, or unequal representation. The simplest way to understand bias risk is to think about who is in the dataset and who is missing from it. If a voice recognition dataset includes mostly speakers with one accent, the system will often perform worse on other accents, not because of intent, but because it never learned those patterns well. If a hiring dataset comes from a company's past hiring decisions, it may reproduce the company's past preferences, including unfair ones, because it learns what the company historically selected. Bias risk also shows up when the data labels reflect subjective decisions, like what counts as suspicious activity or what counts as good performance. Representation is a major bias risk area, and beginners can evaluate it without heavy math by focusing on coverage and balance. Coverage asks whether the dataset includes the full range of people, situations, and environments the model will face. A model trained only on weekday traffic patterns might fail on holiday patterns. A model trained mostly on one region may not generalize to another region where behavior differs. Balance asks whether some groups are so rare that the model cannot learn them well, which can lead to higher error rates for those groups. Even when protected characteristics are not included directly, other variables can stand in for them, like school attended, neighborhood, or job history patterns. Evaluating bias risk is partly about spotting these proxy pathways and recognizing that an innocent-seeming dataset can still drive unfair outcomes. Measurement bias is another common risk that sounds technical but is easy to grasp with a simple example. Imagine measuring productivity by counting emails sent, which favors jobs and communication styles that generate more email, not necessarily more value. In AI systems, measurement bias happens when the data captures a convenient signal rather than the true concept you care about. In security, you might measure risk by counting alerts, but alert volume can reflect tooling and configuration more than actual threat. In healthcare, you might measure illness by hospital visits, but access to care differs across populations, so the data reflects access as much as health. When labels are built from past human judgments, the labels may reflect stereotypes or uneven enforcement, like who gets flagged for additional screening. A practical evaluation of bias risk asks whether the data measures the real thing or a distorted stand-in that varies across groups. Privacy fit is the third leg of this stool, and it is not only about whether the data includes names or obvious personal details. Privacy fit asks whether collecting and using the data aligns with expectations, legal requirements, and ethical boundaries, given the purpose. A key concept here is that personal data can exist even when direct identifiers are removed, because combinations of seemingly harmless attributes can still point back to a person. Location patterns, device fingerprints, and unique behavioral sequences can identify someone even without a name attached. Privacy fit also considers whether sensitive categories are involved, such as health information, biometric data, children's data, or data about protected traits. If an AI system ingests such data, the privacy stakes rise quickly, and the organization must be very clear about why it is needed and how it is protected. A beginner-friendly way to test privacy fit is to ask about the data's journey and the promises made along the way. How was the data collected, and what did people believe would happen to it at the time? Because privacy is often about expectation as much as law. Was consent obtained? And if so, was it meaningful, specific, and understandable, or was it buried in vague language? Is the data being reused for a new purpose, which is a classic privacy risk because it can surprise the person whose data it is? How long will the data be kept, and is that retention tied to a real need or simply indefinite? Who can access it, including vendors, contractors, or internal teams that do not need it? These questions help you decide whether the input requirements fit privacy principles instead of treating privacy as an afterthought. Now pull these three ideas together. Appropriateness, bias risk, and privacy fit are not separate checkboxes, because changing one often changes the others. If you reduce privacy risk by removing certain fields, you might accidentally increase bias risk if the remaining data becomes more proxy-driven or less representative. If you add more data to improve accuracy, you might make privacy worse if the new data is more sensitive than necessary. If you focus only on appropriateness for the business goal, you might ignore that the business goal itself could lead to harmful discrimination if implemented without guardrails. A good evaluator thinks in trade-offs and asks for clarity on what is truly necessary. The goal is not to make data perfect, which is impossible, but to make its risks visible and manageable in a way that matches the seriousness of the use case. A practical evaluation should also consider where the data comes from, because sources carry different risks even when the same fields are involved. First-party data collected directly from users is not automatically safer if the collection was unclear or overly broad, and third-party data purchased from brokers is often high risk because it may be hard to verify consent, accuracy, and provenance. Public data can still be personal data, and using it at scale can violate expectations even if it was publicly accessible. Data scraped from the internet can include copyrighted content, personal information, or biased language patterns that seep into model behavior. Internal operational data, like support tickets or employee reviews, can include sensitive content and subjective judgments that are not suitable for automated decision-making. Evaluating input requirements means insisting on a clear story of origin, permissions, and limitations, not just a file drop. Quality is another hidden influence on all three areas, because low-quality data can create both unfairness and privacy problems. If addresses are frequently wrong for a certain group because of how data was collected, the model might mishandle that group more often, creating unequal error rates. If a dataset contains free text notes, it might accidentally include personal details that were never meant to be used for modeling, such as medical information or personal opinions, creating privacy leakage. If labels are inconsistent across teams, the model learns inconsistent rules, which can show up as unpredictable outcomes that harm trust. Evaluating input requirements includes setting expectations for completeness, accuracy, timeliness, and consistency, and being honest about what happens when the data does not meet those expectations. In beginner terms, if you feed messy ingredients into your recipe, you should expect weird flavors, and you should not pretend the final dish is reliable. It is also important to anticipate how the data will behave once it is inside a model, because AI systems can amplify patterns in ways humans do not anticipate. If the training data contains biased language or stereotypes, a model that generates text can reproduce that style, even if the intended use is neutral. If the training data encodes historic decisions that were unfair, a predictive model can make those patterns look objective by turning them into a score. If the data contains personal details, a model might inadvertently memorize and reveal them in unexpected ways, depending on how it was trained and used. This is why privacy fit and bias risk are not only about what the dataset looks like today, but what the system might do with it tomorrow. A cautious evaluator asks whether the team has considered these behavior pathways and has planned controls to reduce them. A simple way to make all of this concrete is to imagine a student support system that predicts which learners are at risk of failing a course so staff can offer help. Appropriateness would mean the inputs relate to learning progress, like assignment completion and engagement, not unrelated personal traits. Bias risk would include whether the dataset reflects past patterns of who received help, because maybe some groups were less likely to ask for help or were overlooked, and that pattern could become a prediction that they are not at risk. Privacy fit would include whether the system uses sensitive information like disability accommodations or personal messages, and whether students understood that their learning activity could be analyzed for this purpose. The difference between a supportive intervention and a harmful label can come down to input requirements and how carefully they were evaluated. This example shows why the evaluation is not just an academic exercise, but a way to protect real people. When you evaluate input requirements in an audit or review mindset, you are looking for evidence that the team has done careful thinking, not just that they can describe the system confidently. You want to see that the purpose is clearly defined, that data elements are mapped to that purpose, and that unnecessary or risky elements were excluded with a reason. You want to see that bias risk was considered through representation and measurement questions, and that privacy fit was considered through collection context, consent, access, and retention. You also want to see that decisions were documented, because undocumented decisions tend to be forgotten, and forgotten decisions tend to be repeated without learning. Even as a beginner, you can recognize whether a team can explain why each input exists and what risk it introduces. If they cannot, that is a signal that the model is being built on convenience rather than responsibility. To close, remember that evaluating data input requirements is one of the most powerful ways to shape an AI system before it causes harm, because once a model is trained and deployed, bad data choices become baked into outcomes. Appropriateness keeps the system tied to a legitimate purpose and prevents it from drifting into unnecessary surveillance or shaky claims. Bias risk evaluation helps you predict who might be treated unfairly and why, so you can push for better coverage, better measurement, and better labeling before the system is trusted. Privacy Fit keeps the system aligned with expectations and rules by limiting data to what is needed and protecting it through careful handling and access. These three checks work best together, like a tripod that keeps a camera steady, and if one leg is weak, the whole system wobbles. If you train yourself to ask these questions early, you will be able to spot risk in plain language and contribute meaningfully to responsible AI oversight even without being a data scientist.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.